Hello everyone. So in today's lecture, we are going to be talking about the atomic structure, the subatomic particles, and writing Nuclide symbols. Be familiar with this image in front of you right now, all 118 elements, and they are presented in the document called the periodic table. By the way, this is the only approved table of elements that you can use for your exams, and there cannot be any handwritten notes on it. Okay, so as you can see, there are 118 elements that we know so far. We could actually get more in the future if we need to. And if you look at the key, it tells you that the number on top is the atomic number for each element, the symbol, which are the two-letter symbol, the fully spelled out name, and then underneath it, the last number, or the last, number in the actual table per element is the actual standard atomic weight. For your information, the standard atomic weight, you don't have to worry about that right now until we're going to start covering stoichiometry. Okay, so for now, the only thing that you need to worry about are the first three things in the box: the atomic number, the symbol, and the name. Okay, so we're going to talk about like metals and non-metals later, but why do we care about these things? Well, the reason why we care about this periodic table is because each one of them is actually made up of an atom. All right, so the smallest distinctive property of an element is called the atom. All right, and the atom is made up of three subatomic particles: neutrons, protons, and electrons. Now, just as an aside, I would like to tell you that there are actually smaller particles, smaller than an atom. We actually have quarks, gluons, so on and so forth. But for our purposes, we're going to be concentrating on neutrons, protons, and electrons. Okay? And again, the reason why the atom is the smallest part of an element is the combination of these three particles makes up an atom. Okay? Just like a human being is made up of one head, two arms, and two legs, normally speaking. All right? So neutrons have an atomic mass of 1 atomic mass unit and also have no charge. Protons have also an approximate atomic mass unit of 1 and has a positive charge. And electrons actually have an atomic mass unit of an approximately 0.005, and they have a negative electrical charge. The atom represented in the schematic here actually is made up of two distinctive regions: the nucleus, which is in the middle here, the center here, and around it, which is way, way, way bigger than the nucleus, is called what we call the electron cloud. And the reason why it's called the electron cloud, the biggest region of an atom, is because it is made up of electrons. Now, electrons don't just randomly populate electron orbitals. They actually are in distinctive orbitals, similar to how the Earth revolves around the Sun. Okay? So electrons again are in the orbital cloud, which surrounds the nucleus. And the nucleus is way, way, way smaller than the region, the electron orbital cloud. However, it carries the mass of the atom because it contains the two subatomic particles, protons and neutrons, that have an approximate mass of 1 atomic mass unit. Now, the reason why we don't consider an electron in terms of atomic mass, especially in chemistry, is because if you look again at the numbers, protons and neutrons has a mass of 1 atomic mass unit, approximately speaking, and an electron has such a very, very small mass, 0.005, and that is why we do not consider electrons in terms of atomic masses. Okay, so again, nucleus in the middle, right here, containing protons and neutrons makes up the mass of the atom, and in the bigger region around it is the electron cloud, which makes up of orbitals where electrons basically zip around at the speed of light. So if I'm going to ask you the structure of an atom of an element, drawing this is going to take you forever. Okay? So the way we do it in chemistry is the way we represent an atom is actually by writing what we call the nuclide symbol, which is shown here. All right. So if you look at the electron symbol, or the nuclide symbol, specifically speaking, in the middle is the actual elemental symbol, in this case He. He is helium. On the lower left is the atomic number, which is the number of protons of every single helium atom, which is number 2. So there are 2 protons in every single helium atom. And because helium is number 2 in the periodic table, we do not normally write this down. Okay, so this 2 here is normally omitted. On the upper left is the mass number. Now, just to give you an FYI, helium in this case has a mass number of 4, and this 4 comes from the number of protons and neutrons right here. Okay, let me change my color here. So there you go. So that's protons and neutrons. Let me erase that just so that it doesn't look weird. All right, so however, having said that, I would also like to tell you that there are other atoms of helium actually that can have a mass of 5. There are also helium atoms out there, and again, I'm sorry, this is taking me forever because this is a cursor that can have a mass number of 6, and so on and so forth. Okay, the idea here is this helium that has a mass of 4, this helium that has a mass of 5, this helium that has a mass of 6 are still atoms of helium, because guess what? They still have, each one of them have 2 protons. And again, that is why the atomic number is the identifier for the specific element. Having said that, look at the mass here. We have 4, we have 5, we have 6. So which means to say that in this case, this helium atom here has 2 neutrons. And the reason why I got 2 neutrons is 2 protons, right? You subtract that from this number, I should get 2. So that means there's 2 neutrons here in this atom of helium. In this atom of helium, it has 3 neutrons as opposed to 2 here. And in this atom of helium, we actually have 4 neutrons. So this one has 2 neutrons, 3 neutrons, 4 neutrons. Still the same atom, helium. These 3 are called isotopes. And so isotopes then in this case are atoms of the same elements because they have the same number of protons. However, since they have different number of neutrons, they are called isotopes. Okay? I'm gonna erase this. Let's see if this works. Now, so we covered the number on the lower left and the number on the upper left, and then we actually have this sometimes number on the upper right. Now again, I say sometimes because sometimes there's no charge for an atom. In this case, where does the charge come from? The charge comes when you compare the number of protons, which are positively charged, and you compare them to the number of electrons, which are negatively charged. Okay? So there's a distinct possibility that there's no charge, which means it's neutral. It could be positively charged or it could be negatively charged. So, in this case, why is this helium atom have a positive 2 charge? Well, again, let's look at this. So the number of protons for helium is 2, right? And the charge of protons are positive charge. Now, if I compare this, how do I get a positive 2 charge? The positive 2 charge comes from the fact that I have 0 electrons, right? So if I have 0 electrons, there is nothing negative that negates the positive 2 charge. So if I add this together, plus 2, right? Plus 0 or plus 2 minus 0 if you want to do it that way, the overall charge in this case is positive 2. Okay? Now, this could also be neutral, no charge. How is that possible? Well, if I have positive 2 charge for the 2 protons, if I have 2 electrons which are negative, the charge in this case, if I subtract these 2 numbers together or add them together, whichever way you prefer, is 0. Okay? I could also have a negatively charged particle here. How can that happen? Well, if I have, again, the number of protons doesn't change here, folks. And let's say I added 2 electrons. So now I have positive negative 4 in this case, right? I have positive 2, negative 4. Guess what? I have more negatively charged particles than positively charged particles. And this is where I get a negative 2 charge. Okay? Let's do some exercises actually involving this thing. So we're going to go back to the first one. So I could definitely ask you a bunch of questions about nuclide symbols. So let's say I can give you a list, and let's say I give you a particle that has 10 protons, okay, 12 neutrons, and 8 electrons. What is the nuclide symbol for this particle? Well, the reason why we're in this page is because the number of protons tells us what element it is. So element 10, atomic number 10 is neon. So therefore in this case, this would be symbolized as neon. And now we're going to take the atomic mass, and the atomic mass, folks, is just these 2 numbers together, protons and neutrons. So we have 22. And now here's the puzzling part. Is there charge for this particle? And the answer is yes. Because if you compare protons and neutrons, there are more protons than electrons, And so therefore, since there are more positive charges, the charge for this thing is, there's 2 more, it's positive 2. Okay? Well, how about if I give you a nuclide symbol, and then you have to predict, in this case, the subatomic particles, and you should be able to be very, very familiar from going back and forth. So let's say I give you carbon, and I give you a carbon, in this case 14, and I'm going to give you a charge of +4. Will you be able to list the number of protons, neutrons, and electrons? I hope you could do. Okay, so in this case, the number of protons in this case remains fixed. The number of protons for carbon, any carbon, is 6. The number of neutrons, folks, is 14 minus 6, which is 8. And why did I do that? Because this mass is the sum of protons and neutrons. So 8 plus 6 equals 14. Now here's what's going to kill you. Electrons. Folks, positive 4. That means to say there are more protons than electrons. And so in this case, we actually have 2 electrons. More positive than negative. Alright? So again, be familiar from going from nuclide symbols to subatomic particles, or from subatomic particles to nuclide symbols.